Take a look at an example of chi-squared, and this is a test for independence. And I've got stating the hypotheses, finding the test statistic, p-value, conclusion. I've got my 4 steps to my 4-step method. So the first step are my hypotheses. And in this problem, researchers studying the link between prenatal vitamin use and autism surveyed the mothers of a random sample of children aged 24 to 60 months with autism and conducted another separate random sample of children with typical development. The table below shows the number of mothers in each group who did and did not use prenatal vitamins during the 3 months before pregnancy, and that information is here. Now, since it's actually looking at 2 separate samples, and I'm wondering if the distribution for the 2 groups is the same, I might actually call this homogeneity instead of independence, but name doesn't matter too much. The math will look the same either way. And what I'm really wondering is, are the percentages of individuals that have autism for the vitamin group, is that the same as the percentage of individuals that get autism for the no vitamin group? In particular, I'm wondering if taking these prenatal vitamins has some sort of a relationship. So that's not a causal relationship, but some sort of a relationship between. So there's correlation, but not causation. And the alternative is that there no relationship. Alternative, there is a relationship. Won't tell us exactly what that relationship is, but it'll tell us there's something going on. Whenever I'm doing a chi-squared test, I'm always testing for some sort of a difference. The test itself ends up being a right-tailed test, but it is always testing for a difference. The model I'm going to be using here is chi-squared. And the degrees of freedom are the number of rows minus 1 times the number of columns minus 1, not counting the totals. So if I'm looking at this set here, then I've got these numbers on the inside giving me 2 rows and 2 columns. So I've got 2 minus 1 for the rows and 2 minus 1 for the columns. I have 1 times 1. I have a degree of freedom of 1 for this model. And the information that they provided me there is my observed data. So I'm going to make this grid, and then let's switch to just the overhead so we can see this better. Observed, no vitamin, vitamin, total. And then I have autism, no autism, and total. I had, for totals, 254, 483 as the overall total, 181, and 254, and this number here has to be 229 because it has to add up to that correct value. This has to be 302. And notice if I have just one of these inside values, I can find the rest with addition and subtraction. That's what it means when it says the degree of freedom is 1. So if I look at the screen and see that this is 111 in that cell there, I can get the rest for free because 111 plus 70 would give me 181. 70 plus 159 would give me 229. 111 plus 143 would give me a total of 254. I only needed one inside value to get the rest with addition and subtraction. I have a degree of freedom of 1. And my numbers match up with my chart here. This represents my observed. And maybe there's a relationship in here. That's what we ultimately want to test. And I'm going to compare this to an expected, where I keep all of my ratios the same. And some key parts of this table for the expected are going to be identical. In particular, my totals are going to stay the same on the outside. This will be 254. This is 229. This is 483, 181, and 302. To find any of the inside values for the expected, for example, the expected for no vitamin and autism, you will take the total for the row multiplied by the total for the column, and you'll divide this by the overall total. So I'm trying to find this one spot there, no vitamin and autism. The row total is 181. Rows go side to side like you're rowing a boat. Columns go up and down like columns of a building. The column total here is 254. And my overall total is 483. Now, if there is no relationship, then my observed and my expected should be pretty close. 181 times 254 divided by 483. Turn my lamp on here, make that a little bit easier to read. There we go. And that gives me 95.18. So that's that cell right there. 111 compared to 95.18. It looks like there might actually be a relationship here. I don't know what that relationship looks like. Let's keep going through the math and see what comes up. So to find these missing cells, I can just use addition and subtraction. So I can do 181 minus this 95.18 to get this value here of 85.82. To get this value here, I can just go up and down and do 254 minus 95.18. This gives me 158.82. And this last value will work horizontally or vertically. So I'm going to do 302 minus this 158.82. And that gives me 143.18. On any of these values, you could do that same multiplication trick to verify. So for example, to find that 143.18, I could have also taken the total for the row, 302, times the total for the column, 229, divided by the total overall of 483, and it's still giving me that same value. So you can use the multiplication trick to find all of them, but you only really need to do it for up to the degree of freedom number of squares, and the rest you can get with addition and subtraction. So I've got my observed, I've got my expected, I've got my hypotheses here. I'm moving on to finding my test statistic and my p-value. Chi-squared is the sum, this means sum, of my observed values, there are my observed values in this grid, minus the expected squared over the expected. And I can check these off as I go, but I want to make sure that I am pairing these things up. So this 111 here is going to get paired up with the expected of 95.18. So I have observed minus expected squared over expected. And I'm going to keep going. So this next one, I've got 70. That's the observed. And the expected is 85.82. I can do the totals, but you'll notice it won't matter because if I do 181 minus 181, that's just going to give me 0. So I'm really just using those inside numbers. I've got 143 observed, an expected of 158.82. And you could do these in any order. You could go up and down, you could go left and right, you could do some sort of a spiral. It doesn't matter. I do like to check them off as I go along. So these were paired up, these were paired up, these were paired up. I'm down to just these values. 159 minus 143.18 squared over 143.18. I will type this into a calculator and see what I get. And this will give me my test statistic. I'm going to type it in exactly how it looks. So I'm going to type in that first 111 minus 95.18 squared divided by 95.18, and then I'm going to move my calculator up. 70 minus 85.82 squared divided by 85.82. I have 143 minus 158.82 squared divided by 158.82. And finally, I have 159 minus 143.18 squared divided by 143.18. And when I do this, I get a chi-squared of 8.87 or so. Chi-squared is a lot like a z-score squared. To give you a little bit of number sense, if you take the square root of that number, that's a lot like having a z-score of 2.98 or so. So this would be like having an unusual result. I'm expecting a pretty small p-value. Now, this is always going to be a right-tailed test. So if you want to look this thing up in GeoGebra or your graphing calculator or whatever you're using, probability, I'm going to go into whatever I'm using, GeoGebra in this case, probability, and I'm looking at the chi-squared distribution. It's going to ask me for my degree of freedom, and my degree of freedom here was 1. I'm going to choose this option. That will shade this thing to the right, and then, so I'm seeing that it's shading it to the right. So I'm going to choose the shade right option. For the degree of freedom, it's 1. And then I'm going to have a blank spot on the inside. That's your chi-squared number. And the number that it spits out on the outside, that's going to be your p-value. So in this case, my chi-squared was 8.87. And putting 8.87 in gave me a p-value of 0.0029. As always, I've got my conclusion. So compared to, say, an alpha of 5%, you might say this p-value is smaller than an alpha of 5%, we reject the null hypothesis, and we have evidence of a relationship between prenatal vitamins and autism. It doesn't say what that relationship is. It doesn't say that it's a causal relationship. It's just telling me that there's some sort of correlation between these variables. Now, inside of GeoGebra, if you go to statistics and you choose the option for chi-squared test, you get something that looks like this. And inside of this, you can choose how many rows and columns. We had 2 rows and 2 columns. We had a 2 by 2 to start out with. And those inside numbers were the 111, 70, 143, and 159. I'll type those in now. When I do this, it will calculate the degree of freedom, 1, that looks good. The chi-squared value, 8.86, 8.87, up to a little bit of rounding, looks great. And a p-value of 0.0029, that's the same p-value that we got. In addition to this, it will show me the expected count, or my expected table. And I can compare those numbers, 95.18, 85.82, 158.82, and 143.18. So if I'm going through this process by hand and I want to double check my work, GeoGebra is a really nice way to double check your work. Let's go into MyOpenMath and let's type in these results. I am testing for difference. My test statistic, 8.87. So GeoGebra's giving me 8.86. We'll see if it takes that. P-value, I got 0.0029. And my p-value was low, so we rejected the null hypothesis and had evidence of the alternative. When I did this, full points, even for that 8.87 with just that tiny bit of rounding, this is looking pretty good. So again, this is sort of that process of going through to do chi-squared. This was a test for independence, and it's still using the same chi-squared calculation of observed minus expected squared over expected. Hope that helps out. As always, I'm around for questions.